इस वीडियो में हम लोग देखेंगे ट्रांसपोर्ट प्रॉपर्टीज इन गैस। बेसिकली इन दिस वीडियो I wish to describe how a gas can transport momentum, energy or particle from one place to another. The model we have used previously has been that of a gas in equilibrium, so that none of its microscopic parameters are time dependent. Now we consider non-equilibrium situation but still steady state, so that system parameters are not time dependent but still surrounding will be time dependent. The phenomena we want to treat are called transport properties, and we will consider viscosity, which is transport of momentum, thermal conductivity, which is transport of heat, and diffusion, which is transport of particle. First, viscosity. It is the measure of the resistance of a fluid to the deformation produced by a shear stress. For straight, parallel and uniform flow, the shear stress between layer is proportional to the velocity gradient in direction perpendicular to the layer. Shear stress is directly proportional to minus dV by dz. अगर ये प्रोपोर्शनली अगर हम लोग हटाते हैं तो ये कांस्टेंट आएगा eta, which is called the coefficient of viscosity. Now consider a scenario in which fluid is flowing between two plates of area A lying in xy plane. A shear stress Txy, which is force upon area, is applied to fluid by sliding the top plate over it at a speed u while keeping bottom plate stationary. A velocity gradient dux upon dz would be there, so that it will be 0 near bottom and u at top. As we know, viscosity is defined as F upon A is equal to eta dux upon dz, whose unit is Pascal second, where force is rate of change of momentum and hence transverse momentum is being transported through fluid because molecules traveling in the plus z direction move from a layer in which ux is smaller to one in which ux is larger. Hence they transfer net momentum to that layer in minus x direction. Molecule traveling parallel to minus z direction have opposite effect. Txz is flux of momentum, and note that there must be minus sign involved because the momentum flux must be from region of high transverse velocity to region of low transverse velocity. Therefore the momentum flux would be this. Previously we know that the number of molecules hitting unit area per second is this. Now consider molecule traveling at an angle theta to z axis. Then molecule crossing a plane of constant z will have traveled along it on average distance lambda. Since their last collision they have traveled lambda cos theta parallel to z axis. So net momentum transfer would be this, minus m dux upon dz lambda cos theta. Hence total x momentum transported across unit area perpendicular to z in unit time is momentum flux. So the momentum flux would be this, and after calculating we will get this, and comparing this value from pi x is equal to minus eta dux upon dz, we will get eta is equal to 1 upon 3 nm lambda v.